Well, welcome back. Everybody have a nice break? Yes? There, we fit all up the top nice. That's pretty nice. Okay. Oh, but it's gonna. Okay. So, anyone have any questions about homework 5, chapter 5 and chapter 6? Okay, that's quiet. I guess we'll move on. We ready for today we're doing chapters 7 and 8. So chapter 7, we're gonna move from, we've already done 1 sample t-test, now we're gonna do 2 sample t-tests. And then chapter 8, we're gonna do effect size and power. Now I sent out an announcement. Did you guys get the announcement about installing G-Power before class today? Give me a thumbs up if you were able to get that installed and a thumbs down if you were not. Hillary, up. Okay, great. Fabulous. Okay, let's start off with chapter 6, which is 2 sample independent groups t-test. Now, I have been working on the slides, kind of updating them a little bit. So if you have downloaded these slides from online, they'll look, a couple of the slides, not many, but a couple of them might look a little different. So I think you'll be okay. I will put this updated one up online at the end of class, but I was working on it through the morning and I didn't get it uploaded because I had too many clients that had meetings go over, which is an okay problem to have. So t-tests, we're going to do t-tests just like we did before. We're going to calculate a t, and we have a critical value, a p-value, hypothesis. The only difference now is we have 2 groups. So we talked about what are the limitations of a z-test, the 1 sample z-test. A z-test is really slick, but what does it require you to know that we don't often know? Undo your mute button, come on. What do we need to know for a 1 sample z-test?
We need to know the population mean.
Population mean.
And the standard deviation.
And the standard deviation. And that is the problematic one, is knowing what the population standard deviation is. Usually if we knew that, we would not be studying it. So instead of a z-test, we usually do a t-test because that allows us to use, instead of the whole population standard deviation, instead we can use the little sample standard deviation. It also allows us to use a little smaller of a sample size still be accurate, and that's by imposing the degrees of freedom with the Guinness-Beer adjustment, shall we call it. So when we do that, 1 sample t-test is a lot easier to do than a t-test in that you don't have to know the whole population standard deviation. But a lot of times it's not less than the best because you only have 1 group and you're comparing it to some, Melissa, right, number from the sky, number that came from thin air. A more powerful design is instead to have a 2 sample design where you might have a control group or a placebo group. Because remember, we're always wanting to document usually a difference. And if we really want to show there's a difference, we need a group that doesn't have the thing we're trying to show causes a difference. So we need a comparison group. So these are more powerful designs. We're going to have 2 groups. It does not have to be a placebo and a control group for 1, but those are more powerful. Sometimes we can compare to other groups like left-handers and right-handers. We don't have to say which one's treatment and which one's placebo. They can just be 2 different groups. They can be observationally different, like if we had people that are left-handed versus people that are right-handed, or they can be experimental groups, like if we randomize some to receive a sugar pill and some to receive a true drug, or therapy that normally takes place versus a newer version of the therapy. So we can randomize or just observe the groups, but either way, we have two groups we're going to compare in the two samples t-test. Now, this is also called an independent groups t-test, a between subjects design, a between groups design, or a randomized group design. Those all are the same mathematical model. We have two groups where we don't have, where they're independent or different. There's something different between the subjects or the groups. Now, what would be something, a scenario that would not be independent groups? What would be something, I mean, independent, sure we can say it, but what would be the opposite or not qualify as independent groups?
Like before and after stuff. Like you weigh before you go on a weight loss program, you weigh after. So it's the same people in both groups.
Yeah, if you have the same people in both groups, because a lot of times a pre-test, post-test, that is not an independent groups design. That is a matched group design. And that's a very powerful design too, and we will get there, but that's not what we're talking about here. Here, these are independent. Another one would be if we went and got married couples and we put husbands and wives were our two groups, and that these husbands were married to these wives. Those would not be independent of each other. If we went and got a sample of people and we put men in one group, women in one group, if we just got a random group of people, then the men and women would be independent. But if instead we sampled households or married couples and then separated them into the men and women, that would not be independent. It's very important to know the difference. They're both fine to do. You just need to know which situation you are in your research. And it will be different in different studies. But today we're going to talk about independent groups, where the two groups of people are not connected to each other in any systematic way. Good. Okay, so the steps of these tests are very familiar. Here we have them. Step number one, we're still going to write our null and our alternative hypothesis. When we write those, they're in the blue box here on this slide. Our null hypothesis is that there is no difference. So we can write this like 4 or 5 different ways. There's 3 different ways showed on the slide. One way is to say, now remember, the hypothesis is about the whole population, not just about our sample. So it's our hypothesis is in the population, there is no, if we could measure everyone, there would be no difference. So we can write it difference, and then it has this little subscript mu is equal to 0. Or we can write that the two mu's, and here there's mu sub 1 and mu sub 2, but you could do mu of men and mu of women. I would suggest not doing 1s and 2s. I would suggest doing words or letters to remind yourself which one's which. But you can write it either that the two mu's are equal, or you can write it that when you subtract the two mu's, you get 0. Remember, null hypothesis is nothing's going on. If nothing's going on, there is no difference. So the mu's are either equal to each other, or the other way to write it is when we subtract them, we get a difference of 0. Now, our alternative hypothesis can be a 2-tail or a 1-tail. The way it's written in this box here, what would this be? A 2-tailed alternative or a 1-tailed alternative? It's 2, because we have the not equal sign. We have the equal sign with the slash through it. If I wanted to do a 1-tailed test, what symbol would I use instead? A greater than or a less than. We'd have to use one of those greater than or less than alligator symbols. Okay, but you can do a 1-tailed test. The same thing applies. As one sample test, you want to use the not equals, the 2-tailed, unless you have really strong evidence and criteria to back yourself up to do one. So on the homework, we're always going to do a not equal 2-tailed test unless otherwise stated. We're going to still calculate a t statistic, and this t statistics in this green box looks pretty much like every other one we've seen. It's the estimated sample value minus the hypothesized null hypothesis value divided by the standard error. That general format's the same. Exactly what we put in there will be a little bit different. Now there's an asterisk under that green box. Just like in a t-test, what happens with the t-test? If we have a small sample, our degrees of freedom, oh, do we have, Kelly's calling me. I didn't see that she needed to be added. Good, we'll get her on there. Good. Oh, come back. Okay, so if our sample size is 10, our degrees of freedom are 9. What happens if our sample size is 100? If our sample size is 100, our degrees of freedom are 99. The bigger our sample is, the less the subtracting 1 makes a difference. And if we remember our t-test, the bigger the degrees of freedom, the more that t curve matches the z curve. So that's why this little asterisk is down here. If our sample size is bigger than 100-ish, this can be treated as if it was a z score, not just a t score, but we can use the same table. We're going to look at the bottom of that t table today. So just like other hypothesis tests, we're going to set our alpha level. What's our default alpha level if we have no other information to go on?
0.05.
0.05, that's our default. What are we going to go? And we already said we're going to go with 2 tails most of the time. We're going to get our samples, collect our data, find our rejection region. All that's the same as before. The difference here is how we exactly calculate that t statistic. Now, before we look, well, let's look at this in general. You don't have to worry about writing this down. It's on the formula sheet, and I'll show you where to get it, okay? So these orange boxes are called the separate variance test, and they require that you have something called homogeneity of variance, HOV. The purple boxes are another alternative, and this is if you have different sample sizes or you don't have homogeneity of variance. So there are 2 flavors or kinds of 2-sample t-tests you can do, and it's based on whether or not you have balanced groups. That means the groups are the same size, and whether or not you have the same spread in both groups. That's called homogeneity of variance. So we're going to look at those formulas a little bit different. So in both, either the orange or the purple, either of these separate variance versus pooled variance versions of the 2-sample t-test, they both have a t statistic and they both have a degrees of freedom. We're going to look at these formulas a little bit more in detail on our formula sheet. So this is the formula sheet that I put together for this class. You can find this by going to our class website and scrolling down. Right before this table of the chapters, it says formula sheet. You click on there. Here is our formula sheet. Now, you are welcome to print this off and use it on every test, to have it in your binder or folder for future reference. It's the formulas that you need to run t-tests and z-tests on this first page for comparing means. So before we did the z-test and the t-test for one sample. So if you look at the top of this grid, this layout, there it says for one sample. On the side it says x equals measurements in a sample, mu is the population mean. So if we're doing a 1-sample test, we're trying to estimate this, we're using the sample average as our best guess, our point estimate. And our critical value, we could either use z or t. If we're using z, how do we make the standard error for the mean? We use sigma. If we don't know sigma and instead we're using s, the sample standard deviation, then we do it as a t-test. Now there's notes here at this last column of this table. So the first box says, use if you know the population standard deviation or when the sample is very large. What do we mean by large? How large? Over 100-ish, yeah. So that's this top line, using the z statistic if you know the population standard deviation and or you have a very large sample size. In other cases, when we have a small sample size or we're using the sample standard deviation, we use the t-test. Now down here, there's this little box that says d equals, that's Cohen's d effect size. And we're going to get to that in our chapter 8 today, but just pointing it out is on here. So the first kind of strip across this table in white, those are the 1-sample t-tests, the z and t-tests we've already done. If you go to the bottom of the page, this is for 2 independent samples, not paired. And so here are all the formulas that we're going to need for doing the 2-sample t-tests where they're independent. Now in the center of this page, let me just point out that it's gray in the center. This is for matched pairs. We'll come back to this chapter, I think in chapter 11, I think it is. but we're going to hold on. Matched pairs we're going to come to after we do correlation. But so right now we've done the top, and now we're going to do the bottom, skipping the middle. So here, notice we have a Z. When would we use a Z? When we know both population standard deviations, or when both samples are large. Sounds like pretty much the same criteria, but instead of having one population, we have two populations. So that's when you can use Z. T, we're going to use in all other situations. Now, I said there were the two different flavors or kinds of t-tests. Get this to fit all on one screen. No, not that one. This one. So over here, let's look at the notes. The separate variance test is appropriate when you have equal, what does little n mean? Sample sizes. When we have equal sample sizes, but we violate homogeneity of variance. Also, if we have equal n's, we can do this if the bigger sample has the smaller standard deviation. That's the separate variance test. And in R, you say var dot equals false to get this option. The variances are not equal. They're separate variances. If we have populations that have the same amount of spread, that means homogeneity of variance. Homogeneity means the same, variance is spread. Homogeneity, if the two groups have about the same amount of spread, then the option we use in R is var dot equal is true. That's the pooled standard deviation. Because the spreads are about the same, we can pool them to get a more accurate estimate. Also, we can do this when the sample sizes are not equal and the larger sample has the larger standard deviation. So these are the two, you have two independent groups. You have to decide which one of these versions of this test you're going to do. And it's based on sample sizes being equal or not equal and spreads being equal or not equal.
Hey, Sarah?
Yeah.
In the text, it seems like it said you could use the pool if the sample sizes were equal. Maybe I just misread it.
Yes, sample sizes are equal. I think this one's supposed to be unequal right here. Yeah, but the pooled, you have to have homogeneity of variance. Homogeneity of variance. So we're going to test homogeneity of variance with Levine's test. We'll get that in a second.
So we just need to make a note on that, if
I think that, let me get back to you on that, and I'll get the corrected one up. I can't believe that there's still an error on this one. I've been using this one for like 8 years. That would be crazy. So let's go back to our slides. Anyway, so here are, on this formula sheet, you can get all the formulas all in one place. Life can be easier for you. Okay, so let's go back to this slide. Right, so the separate variance. Now let's look at the top. What's on the top of this t-test? The first set of parentheses has what in it? X bar. What's X bar?
sample mean.
The sample averages, the sample means. So we take the two sample means and we subtract it. We say, how different are these samples that we observed? So this is the difference that we observe. Now what's in the second set of parentheses? Mu minus mu. What do we hypothesize that the difference is? What does the null hypothesis see? Null hypothesis say, it's a tongue twister. Null hypothesis says there's nothing going on, there's no difference. So this second set of parentheses is almost always 0. You can do other options, but it's very, very rare. Almost always the two sample test is having a null hypothesis that there is no difference, no difference. So mu minus 1, mu1 minus mu2 is 0. So that's why sometimes you'll see the formulas missing this part, because what happens when you subtract 0? Nothing. So often this part is left off on a formula because it's 0. So on both of those options, the orange and the purple, the top of the t-statistic is the same. It's the bottom that is different. The degrees of freedom are slightly different. For the separate variance test, the degrees of freedom are the combined sample size minus 2. Oh, this is making me nervous. Anyone else nervous? Let's go to the textbook. We had this wrong on an early version of these slides, and the old version keeps cropping its head up. Seven. We are going to the hard copy source. Okay. Let's go to the summary. Okay. Separate variances when the sample size are not large. And here's our formula. So which one does, let's see. S1, S2. That is the separate variance. Yes, separate variance. Sample sizes are not large. Substitute S for sigma. Homogeneity of variance. The pooled variance is this one. When we are assuming that the spreads are the same, we can pool them. To do this, we have to get the pooled standard deviation, and then we get these nice formulas, which we personally will use this top one. The computer uses this bottom one. So here it is all put together. Okay. Equal size, if your groups are equal size, that even simplifies more. Okay. All right. I will double check let's do an example. So here, yeah.
Is it the degrees of freedom that are flip-flopped on the slides?
I think they are.
I'm thinking so too. So for
Yeah.
the pooled variance, that one should be the easy degrees of freedom, right? The N1
Yeah.
plus N2 minus 2.
Yeah.
So I think they just might be flip-flopped on the slide, but I think your formula sheet is
Yeah.
right.
Yeah, I think it's this one. And like I say, these accidentally were put in wrong on the first version, and we fixed it, but it keeps cropping up.
But I definitely think your formula sheet looks right.
Yeah, the formula sheet has been, let's see, edit text.
But I think the DF formulas just got flip-flopped on this slide.
So let's.
Maybe I'm wrong, but that's kind of what
I think you're right. As a teacher, that's like worst case scenario when you're like, no, I'm telling my students wrong.
I know.
So there we go.
Yeah, I think they just got flip-flopped.
Yeah, the pooled variance has easy degrees of freedom. It's the combined sample size minus 2. Now, I thought degrees of freedom were minus 1. Well, when you have one group, you minus 1. And when you have two groups, you have to minus 2 from the combined sample size. With separate variance tests, you have to do something more complicated. Now, in your textbook, I'll just point this out. After the summary, I think it comes, isn't there a section on the Welch's degrees of freedom? Or it's in section B. They show you the formula. So the degrees of freedom for the separate variance test is a little bit more complicated. It's actually a decimal number. Degrees of freedom are a decimal number. That's like, hurts my head, right? Where is it? I thought it was in it's really hard for me to see this. I think it's in the advanced material after section B. Yeah, right there. Okay. So when you do the separate variances test, it is also called, so here's separate variance test, it is also called Welch's test. And that's what R calls it, is Welch's test. And the degrees of freedom is this nice, simple, easy to memorize formula. No, it's not easy to memorize. I don't memorize it. But there's this formula for, where did it go? Come on, come back. For doing the degrees of freedom. And it makes the degrees of freedom a decimal number a lot of times. So here, now you don't need to memorize this formula. Please don't worry about memorizing it. But when you do the separate variance test, your degrees of freedom are not going to be the combined sample size minus 2. They're going to be small. It's going to be smaller than that. So notice how the degrees of freedom are written here. The degrees of freedom in this slide, it's not giving you that Welch's ugly formula. Instead, it's telling you the degrees of freedom are going to be less than the combined sample size minus 2, but greater than, any guesses what MIN means? It means minimum. So our sample size is somewhere between the smaller of the two sample sizes minus 1 and the combined sample size minus 2. Now, what if my sample sizes were 5 and 5? What's the biggest the degrees of freedom could be? Sample size 5 and 5. Combined sample size is 10. Take away 2 is 8. 8 is the most the degrees of freedom could be. Then what's the smaller of the two sample sizes? They're the same, so it doesn't matter. Now take away 1. You get 4. So if I was doing a separate variance test with these orange formulas and I had two sample size 5s, 5 and 5, my degrees of freedom are going to be a decimal number between 4 and 8. The number it is it 5.1? Is it 7.3? The number it actually ends up being between 4 and 8 depends on how uneven the samples are, how uneven their sample sizes are, which in this case they're the same, but also how uneven their spreads are. And we're going to let Welch's formula figure it out, and R is going to spit it out to us. If you have to do one of these separate variances by hand on the homework, which you do, I want you to just, you'll do this, so you'll find the smallest it is 4, and the biggest it is 8. Just use the smaller number because that's conservative when you do it by hand. Okay, so do we all hear this? If you're doing a separate variance test by hand on the homework, go with the smallest it could be. So that's the smaller of the two sample sizes minus 1, because that's conservative. When we do this with R, it's actually going to do that formula and find out which decimal number it is between the smaller and the bigger options. Okay. Let's do an example, because we need examples, right? We all love examples, okay? So this is an experiment. When we say experiment, what do we know? Who decided who went in which group? Who is responsible for that? If it's an experiment, it was the researcher. So the researcher has somehow, hopefully randomly, assigned the participants into a drug group and a placebo group. How many do we have in each group here? 5 and 5, nice and easy, yay. 5 and 5, we're keeping the numbers small. So we want to know, does this antidepressant drug for these clinically depressed participants help their depression? So we're going to give the drug to them for 6 months. Now, the placebo group, we are also going to give them pills, and they're going to look the same, and they're going to be packaged the exact same as much as we can, so that they don't know they're in the placebo group. What's that called when we make the placebo group and the drug group be identical in every way we can? It's called blinding our study so that they don't know. That's always a better way to go. It's not always that feasible. But so we have these groups. So we took all the people, all 10 people at the beginning have clinical depression, and then we separate them into these two groups. They get the drug, they get the sugar pills. Go 6 months, and then we measure their depression. And we're going to compare. If the drug works, what should we see? The depression score should be, in this case, lower. Lower means less depressed. What is your eyeball? When you eyeball these numbers, compare the drug group and the placebo group. What do you feel? Is the drug successful? Yes, it's successful. No, it's not. How clear is it? Looking pretty good? Okay, so the eyeball test looks pretty good. But to be a scientist, we need evidence, we need proof. So we need to weigh this evidence or measure this with a ruler. And the ruler we're going to use is the t-test with the p-value. Okay, so I was working, this is what I was adding to the slides. I'm going to pull up R. Here's my R. I think it's good that we practice in R. R is nice because we don't have to do things by hand, so we won't make mistakes as much, hopefully. Okay, so the two packages I'm going to use are Tidyverse and Furniture because they're my favorites and they make life easy. So I'm going to put in the data. So group 1, we can call them drug. Let's do this. They're 11, 1, 0, 2, and 0. Okay, got them right. And the placebo group was 11, 11, 5, 8, and 4. Okay. That makes a data frame. And if I run just the name, I see here's my drug group numbers, here's my placebo group numbers. Okay, so I've just entered them into the computer. The drug group is the concatenated or combined container 111020. Now, to be able to plot this, we need to give it into stacked form. So this is some code that I'm running. Oh, group. Change the names, right? Group drug, group placebo. And it stacks it up. So this would be, this is what we call, this one is the way that the book has it, is the side by side. But if we were running this study, we would probably have one line per person. And we would probably have some more information about each person. But our first person is on the drug, they scored 11. The second person is on the placebo, they also scored 11. Does this first person in this drug group, are they connected in any way to the first person in the placebo group? Are they the same person? No. So if you put them on the same line in a data set, it thinks that they're the same person. So that's why I wanted to rearrange it from 2 lists to 1 list. So we have 2 variables here. What kind of variable is their score? What type of variable is this score? Nominal, ordinal, interval, ratio. Is it nominal? If it was nominal, we just have categories that had no order. Is it ordinal? Well, there's order, but is it categorical or is it continuous? We don't know how it is measured, right? We're not given a lot of background information. To do a t-test, you have to assume that it's interval, ratio, continuous. You have to. Whether or not that's a good idea is another conversation altogether. Let's assume that this is a very well-known, well-studied, psychometrically valid and reliable measurement tool, and that we can treat the scores as interval, ratio, continuous. Now, if you are doing your dissertation and you decide you're just going to put together some questions and give them to people and add them up and make a score, can you treat your new score as interval, ratio, continuous? No. A whole dissertation would be proving that. So when you're planning your dissertations, you need to go out. Part of your lit review is to find measurement scales that have already been validated and shown reliable with psychometric evaluation. Okay. If you want to do that, that will be your whole dissertation, to develop a new scale. I'm not such a proponent of that, but you can, because it's a lot harder than it sounds, and it ends up taking longer than you probably want your dissertation to take. But I've helped people with it, so you can. All right, so when you have a data set, this is called a tidy data set. Tidy data has 1 line per observation, 1 column for each variable. We have 1 column that designates which group they're in, another one for their score. So their score is, we're treating it as continuous, interval, ratio. What about the group variable? What kind of variable is group?
Nominal.
Nominal.
Nominal. Is there any order to it? Well, it doesn't really matter if there's only 2 groups. So we could also call it binary or dichotomous. All right, so DF, I'm calling this DF long. DF is standing for data frame, and we could call it Fred. Okay, so I can use my furniture package to make a table. Now, here's something I haven't shown you. In furniture, you can add the option. If you don't say this option digits, furniture will give you your means and your standard deviations to 1 decimal place. Is 1 decimal place good enough? Sometimes, how can you get more? Well, you can come into the parentheses of our furniture table 1 and put a comma, and then the option is digits, and tell it how many digits you want. We can ask for 3 digits. You can ask for 12. You probably don't want to, but that's how we can get more decimal places. So looking at the average, the drug group average was 2.6, the placebo was 7.8. Does the drug reduce depression? 2.8, 7.8. It looks like they're different. Let's look at the standard deviations though. What are the standard deviations for the drug group? The spread is over 4.5, it's 4.6. What about the placebo group? 3.3. Here I've made a box plot. Now here, let's see. Now that I labeled it, it'll come up. There we go. So here's our drug group. Here's our placebo group. Are they different? It's looking likely, right? How much overlap is there? Ooh, what about this dot way up here? What is that dot? There's one person. Remember our data? We had one person that was still 11 in the drug group, but all these other numbers were tiny. So there's a little bit of overlap. Now, is a sample size 5 and 5 probably good enough for a dissertation or a peer-reviewed article? Probably not. It's okay for a pilot, maybe, but that's pretty small sample sizes here, regardless. Okay, so there is our data. It's very handy to give your summary statistics and plots of your raw data. Always plot your data first. Always summarize it first. It will help you understand your data, your variables 1 at a time and 2 at a time. So when we're deciding which version of the t-test to do, we need to know, is there homogeneous variance? Our groups are the same size, so we don't have to worry about that. But look at the spread in the 2 groups. Again, back to the standard deviations. Do they have the exact same standard deviation? It's not exactly the same. If we look at these boxes, are the box plots spread exactly the same? No. But is it close enough that we can assume homogeneous variance? That's the more meaningful question. And the way we answer that is with Levine's test. Levine's test is a test where the null hypothesis, nothing going on, is that there is no difference in the spreads. That the 2 groups have essentially close enough to the same standard deviation. Now, they're not exactly the same, 4.6 and 3.3-ish. They're not exactly the same, but are they close enough we can work with it? That's what Levine's test is answering. So Levine's test is in R, is in the CAR package. CAR is for companion for analysis and regression. It's a nice package. And the way you do that is we are going to always start with the name of our data set. We're going to pipe it into the CAR packages function Levine test. Levine is all in little letters and then capital T in the test. There's 3 things that you have to put in the parentheses. The first thing is the formula. The formula has this tilde wave in it. The tilde wave is on your keyboard. It is on the key with the back tick above between your escape and your tab key. So the tilde wave. In front of the tilde wave, you put the continuous variable you're comparing. We often call that our dependent variable. That's our continuous variable we're comparing. After the tilde wave, you put the name of the variable that shows which group people are in. Okay, so the formula, dependent continuous variable, then tilde wave, the name of the grouping variable. The second thing we have to put in is what the data is. Now, usually when we have the pipe lets the data flow to the next step. That works for all the tidyverse functions. Tidyverse functions expect the data set to be the first thing in the parentheses. But some of the older functions didn't. Here, the data set is supposed to be the second thing in the the second thing in those parentheses listing. The way you work with that is you have to put a period to say, this is where we want the data to flow to. See, here's my period. So this period says my data set from above is going to flow into this spot, because for Levine's test, it wants data to be the second thing in the parentheses. And then Levine's test has some options. The default on this Levine's test is to do the median, if their spread around the median is the same. But for the t-test, we need to know if the spread is the same around the mean. So you have to add this other option to make it work right. You have to do center equals mean. So when you run that, it will give you Levine's test for homogeneity of variance. It actually prints out what it is. Isn't that nice? And then here we have some information. Okay, so this last thing, what do you think this last thing is? Looking how it's labeled. PR is usually probability. This last thing is our p-value. The p-value is testing the null hypothesis of nothing going on. They're the same spread. Now, this is an f-test. We have not talked about f-tests yet, but it is an f-test. The way that you would write this out, now a t-test has 1 degree of freedom. An f-test has 2 degrees of freedom. Can anyone find the degrees of freedom on the printout? The degrees of freedom are stacked up. So when there's 2 degrees of freedom, there's a first one and a second one. And in this output, it stacks them up. So if I was going to type this, I would say F, and then in parentheses, I have to put both degrees of freedom, 1, 8. This is APA style too. So you say F, and then in parentheses, the 2 degrees of freedom, 1, 8. Then you say what the F is equal to. Our F value in this one is the center number. It's labeled on top, F value, 0.2. We're only given 1 decimal place. And then usually we give everything to 2 decimal places, except for p-values to 3 decimal places. So how will we report this p-value? Do we report the 0 in front of the decimal place? Not with p-values. And we're going to go to 3 decimal places. So it's going to be point, what are my 3 numbers going to be? 6, 6, round up 7.
Hey, Sarah, why
Yes.
is it just 1 degree of freedom is our lowest? I thought it was the 5 minus 1 or the 4.
Beautiful. The degrees of freedom that those formulas on the PowerPoint that we had, those degrees of freedom are for the t-test. This is a preparatory step before we do the t-test to decide which t-test we should do. So there's more than 1 p-value in this process. So we want to test, do the averages of these, the depression averages, do the depression averages different in the drug group versus the placebo group? To test that, we have to decide, are we going to do a separate variance test or a pooled variance test? So the preparatory step is, are the spreads the same, to help us decide which test to do? So yes, the degrees of freedom for the F test, let me pull our slides back over here. These degrees of freedom, either the combined sample size minus 2 or the smaller sample size minus 1, that's the degrees of freedom for the t-test. What we're doing right now is Levine's test to decide which of these 2 we need to do for the t-test. Does that help, Melissa? Okay, so here we come back to our f-test. So this is Levine's f-test. Is it statistically significant? Is it significant or not significant? Significant? Not significant. I see a couple thumbs. Not. Laura, what do you think? Hillary?
What's the alpha?
What alpha should we use? That's a great question. What alpha do we use if we don't have any other information to go on?
0.5?
0.05.
0.05.
It's not littler. It's not littler. So there's no, so the null hypothesis is nothing going on. The spreads are the same. So here we would, our conclusion for this is that Levine's test found no violations to the assumption of homogeneity of variance. There. So there's no evidence that it to violate that or to go against the homogeny of variance. The null hypothesis is nothing going on. The spreads are the same, and we can't disprove that here. That's a nice thing to have happen. We don't always want to reject or find violations. In this case, we are totally happy that Levine's test found no violations of the assumption of homogeneity of variance, which is usually abbreviated HOV.
So in our homework, when we aren't using this, we have to calculate it all out.
You don't have to do Levine's test by hand. On the homework, the book problems that you start with, the book problems will tell you they will say, do the separate variance test, or they'll say, do the pooled variance test. They will tell you which one to do until you get to the point where you have Eno's data set. And when you have Eno's data set, you can run this
Okay.
to decide. And again, what comes first in the formula? The first thing is the continuous dependent variable that you're comparing the averages on. And the second thing is the two group variable. So this could be like gender or coffee drinkers, not coffee drinkers, a two group variable. And so Levine's test found no violations of homogeneity of variance. So in this case, which one of these tests do we want to do? This is our decision factor. Are we going to do a separate variance test or a pooled variance test?
Pooled?
Pooled.
Pooled. This tells us the pooled test is okay to do. So what would be our degrees of freedom for the pooled t-test? 5 and 5 combined is 10, take away 2, it should be 8. Now, I'm going to show you how to do it in R because, you know, R is nice, it's easy, it does it for us. Okay, so this is how we do Levine's test. Check out how we do a t-test. We start, as always, with the name of our data set. We're going to pipe it into t.test. Did we use t.test before? We used it with the one sample test. When we did the one sample t-test, what did we have to do before the t.test? We had to pull the variable out, and then in the t.test, we had to say mu equals a number. Now, we're using t.test again, but we're doing it differently. You don't pull the variable out. Instead, you write the formula. This formula for the t-test is the same formula we use in Levine's test. The first variable is that continuous dependent variable in front of the tilde wave, and then after the tilde wave, we put the two group variable, the categorical two group variable. And again, this is an older function, so we have to say that the data flows down to the second entry by saying data equals dot. The data flows to the dot, the period on your keyboard. Now this is where you say which test we're going to do. Equal or not equal. So if I pull up that formula sheet, where's our formula sheet? Oh, it's on the slideshow too. Here's the slideshow. Oh, it's kind of tiny there. Let's get it big. Oh, there it is. Come back on the formula. So if we have equal spreads, Levine's test is great. Then we say variance equals is true. If we don't have equal spreads, if we violate homogeneity of variance, we have to say var dot equals false. We have to choose which one we're going to do. Now, if I say true, so that's saying yes, we can treat the variances as if they were the same. Were the spreads identical? No, like never. But they're close enough that we can treat them as if they're equal because they're close. Notice it says 2 sample t-test. Watch what happens if I forget to put that part on. Ready to watch? What happens if I forget to put it on? What does it say? Welch's 2 sample test. The default is variances are not equal, the spreads are not equal, and it does the separate variance test. The separate variance test is also called Welch's. Notice what are the degrees of freedom here. The degrees of freedom are a decimal number in between 4 and 8. So if you violate homogeny of variance, you put false here. Don't treat the variances as if they're equal. And it does a Welch's test that gives decimal degrees of freedom. But if you do Levine's test and you find no violations of homogeny of variance, then you can treat the variances as if they're the same or same-ish, and then you will get combined sample size minus 2 as your degrees of freedom. Okay, so what's the decision point? How do you decide whether or not you treat the variances, the spreads, if they're the same? How do we decide?
The p-value of Levine's test.
The p-value of Levine's test. So if the p-value is big, we say they're the same. If this p-value is small, how small? Less than our alpha, which is usually 0.05, then we'd say don't treat them as equal, and we do the Welch's adjustment or the separate variance test.
So if the p-value is smaller than the alpha, then we don't treat them the same.
We don't treat them the same. We say there were, in that case, if our p-value had been tiny, we would say Levine's test found evidence of violations of the homogeneity of variance assumption. And then we would put it, now that I'm just going to make some numbers up here, okay? So a separate variances or Welch's t-test was conducted. So if there's no, if we find no violations, then we can conduct a pooled variance t-test. So if there's no evidence of a violation, go ahead and do treat them the same, the variances is the same, and do a pooled variances test. If Levine's test gets a tiny p-value, that means that they're not the same spread, so you have to do the separate variances test, which is also called a Welch's t-test. Yeah.
That's a good question. So this is including the score of 11, that outlier, correct?
Mm-hmm. Now, that's a good question. Is it an outlier? What should you do if you have a questionable outlier?
I would throw it away.
You would throw it away. Okay. Thou shalt never throw away data for just being extreme.
Okay.
Just because it's extreme does not mean it's wrong.
Mm-hmm.
Now, if you give depressed people a great drug, is everybody going to do well? No. There is going to be some natural variation or natural spread around the treatment effect. And so that person that got 11, are they just a person who doesn't react to the drug? Maybe. So unless you can pinpoint an error, what if you go back to your files and you find, oh yeah, that was the person that refused to come in and we had to keep calling back and we really don't think that they were taking their pills, if you can come up with that kind of evidence, then maybe you remove the person. But you never remove them just because they're extreme.
Okay.
Only remove them if you can pinpoint an error or a reason that they should be excluded.
Okay.
I want everyone to hear that loud and clear. Don't just throw away extreme data. This has been done in some of the historical studies of global warming. So a lot of the historical temperature data that we have was already aggregated or only one temperature taken. And if they thought it was kind of weird, they threw it out back then and didn't record it. And so we have very little, we know this because there's very little spread in the historical data. But then data we have now, it shows a lot more spread. And it's not necessarily that things have changed, but the way that we've measured and recorded temperature has changed. And so you can get flawed models by throwing out extreme data. Now, bringing back it to COVID, did we have complete data coming out of China? No, not at all. They were only reporting some of the data. And so the models that were based on that flawed data, other than there have been reports that it was terrible modeling, but also the data they were putting in was predetermined, screened, and only some was fed in. So we get a questionable prediction out of it. So if you just throw out the person 11 because they don't fit what you want to have happen, then your results are only gonna be based on that screening of data, pre-screening. And you don't want to do that because then it's not gonna be replicable. Someone else will come along and try to do the same thing and they'll say, we didn't find that, and then you'll be discredited. And I don't know, don't go there.
I guess it just
there.
like it.
Go ahead, Laura.
Yeah.
Oh, sorry. It just seems like it's a little misleading because it's only one, because it's so far out there.
It is out there, but is it reasonable that that's just a person? We only have 5 people here.
Sure.
Melissa, did you have something to add?
Well, I was just wondering, so what the 2 different tests look like as far as coding goes in R. What's the difference between if we do the pooled versus the separate?
The code looks exactly the same, except for the last thing. FALSE, let me spell correctly. Okay.
That makes sense. I knew you had explained that, but I couldn't quite remember it, so thank you.
If we're doing the pool variance t-test, we say var dot equals true. If we want to do the separate variances or the Welch's t-test, we say var dot equals is false. And how do we decide which one? It's based on this p-value. So this is what happened in this, what we actually found, right? So this is an example, not what actually happened in this. But if it had come out like this with a small p-value, then we would want to go use Welch's. And the degrees of freedom are between the smaller sample size -1 and the combined sample size -2. And what number it actually is depends on the asymmetry or the unbalancedness of the spreads, the standard deviations. Now in this case, here is the correctly ran 2-sample pooled variance t-test. Look at its p-value, 0.085. If I did Welch's separate variance test, look at its p-value. How different are these p-values? They're not that much different than each other. If your spread is the same, really close to being the same, then these two will be very close to each other. If you had one group that had a lot more spread than the other, like for instance, just let's play with this. what if we threw out that 11? What if we, Laura, found out that that was a person, he wasn't really taking his pills, I'm going to call it a man, and they weren't, so we decided that they needed to be excluded for not following procedure. Oh, I have to put an NA. Okay, NA. So we decide to delete them. Okay. So let's look at, removing that person, look what happened to our averages. Average of 0.75 versus an average of 7.8. What happened to our averages? They're even more different, right? Look at our spreads. What's the spread in this group? 0.9, it's less than 1, and the spread is here. So the spreads have, not only have the averages gotten far apart, but our sample sizes are 4 and 5, so they're not the same. And our spreads have gotten more lopsided. If I'm going to plot them now, notice that 11 is gone. Yeah, check out those boxes. How does homogeneity of variance look now? A lot less spread in the drug group, a lot more spread in the placebo group. So what happens when we run Levine's test? Levine's test shows that there is, now the null hypothesis is nothing going on, the variances, the spreads are the same. We see, uh-oh, we can reject that, reject the null hypothesis. So this one, this Levine's test is showing, because it's our p-value is 0.03, that's less than alpha 0.05. So we say there is evidence that there is a violation of homogeneity of variance. So we would want to do not the pooled test, we would want to do the separate variance or Welch's test. Now compare the p-values here, 0.004, 0.006. See how there's a little bit more difference in the two p-values because our spreads are different? So here, what would our conclusion be? This is evidence that the two groups have different averages. What about this one? Same thing, still saying the groups have different averages. So we arrived at the same conclusion here, but which one's going to be more accurate as far as the confidence intervals? The more accurate one for this set of data is Welch's, because we have violated homogeneity of variance as shown with Levine's test. So Levine's test happens first. If there's violations, we do Welch's separate variance test. If there's no evidence of violation, we do the pooled variance t-test. I'm going to go put that data back in there. Actually, I can come down to the bottom and run all chunks above. Okay, so we do Levine's test to help us decide which type of t-test to do. Then we run the actual t-test. So there's a two-step process. Levine's test to decide what kind of t-test, and then actually do the t-test. So how would we write these results? Now, if we start at the bottom of the output, it actually works better. So at the bottom, it tells us the group averages. So we can say the depression scores for the drug group, and I could say mean equals 2.8, were lower than the scores in the placebo group. I missed a letter. Geez. So we did see the drug group having lower scores than the placebo group. But what about our test? What's the p-value for our t-test?
It's 0.08, so that, or I guess if you round it up, yeah, 0.085, so that wouldn't be significant.
It's not significant. So the depression scores for the drug group were lower. However, a pooled variance t-test found the difference was not significant. And then we have to put our stats. It's a t-test. And then in parentheses, we put the number of degrees of freedom, which are 8. That equals 1.96. Now, here's a question. Do we put the negative on the, or not? What did our t come out to be, our t value? It's a negative number. But the t value is only negative because the order that we subtracted in. If we had subtracted in the other order, it would have come out to be positive. So because of that, we traditionally, in APA style, do not put the negative sign on the t value, because if we had just subtracted in the opposite order, it would have been positive. Remember, the t curve is like the bell curve, it's symmetrical. So we're going to leave off that negative. And then we always put our every value, we're going to round to 2 decimal places, except for the p-value, we're going to round to 3. Questions, Brian? You're looking hard. Is it just too small on your screen? Hillary, are you doing good? Let's see, Sam, is Sam on yet? Okay. She's good. All right. T-tests for 2 groups. Are the groups different? Okay. So if you were going to write this up, that color is terrible. This green background. Oh, I don't like these slides. These are terrible. Oh, that's even worse. Okay. So if you're going to write up your results for a manuscript or your dissertation, what are the things that you need to include in your write-up? I get asked this a lot. You should, in your manuscript for your dissertation or your thesis or manuscript, we usually have a whole method section and a whole results section, like pages. For this class, we're not going to worry so much about the background, but you should include what are the variables and what is the sample. So here's a way you could do it in 1 sentence. After 6 months, the 5 participants taking the drug scored numerically lower on the depression scale compared to their 5 counterparts taking the placebo. Now notice the way they wrote this. We have the sample sizes, 5 and 5. We have the 2 means, and we have the 2 standard deviations. In the parentheses, if we choose to put the means and standard deviations in parentheses, we can use the abbreviations capital M or capital SD. If we wanted to use those numbers not in the parentheses, just in the sentence, which you can, you have to write out the word mean. You can't use that capital M abbreviation, just to know. And then we need to say what test we did. So here it's been written as a separate sentence. There's a lot of different ways to write this. This is one method. You need to say what test you did. To test the effectiveness of the drug at reducing depression, an independent sample t-test was performed. Now, this next sentence I would not worry so much about. This one says the distribution of depression scores was sufficiently normal for the purposes of conducting a t-test, and it gives skewness and kurtosis and a citation for that. I have never seen that in a real manuscript, mostly because it's something that ends up on the editing floor when you're cutting words to get under the word limit. But if for your dissertation, you might be asked, well, did you meet the assumptions of your t-test? Which brings up the next slide, which is going to be the assumptions. But yes, one of the assumptions is normality. How did I tell you was the best way to judge normality? There were lots of things we could do. Kelly, do you want to go?
Plot it out. Plot it out.
Yeah. That's what I would say. Yeah, draw it.
Draw it out. What kind of plot would you make?
QQ.
QQ plot? Histogram? Box plot? Yeah? I did that for this data, but what's the problem? In this data is we only have 5 observations. How good can you decide, how well can you decide if something's normally distributed with only 5 values? It's really hard to get a grasp for the shape of the distribution when you only have 5 observations. And that's why Shapiro-Wilks is not so great, is because if you have really small sample sizes, it says everything's fine. So you have to be able to defend that the depression scores in general are normal in most populations. And that's why your measurement tool needs to be well validated before you use it, to show that it does function continuously and ratio and interval and normally distributed in general populations, or populations like the ones that you're studying. So that's why you want to pick a tool that's already had all that shown. Like if you're going to do depression, maybe you're going to go with the Beck depression inventory, because it's already been shown that it's interval, ratio, continuous scores, and it's valid and reliable in college students and adults, and that it's fairly normally distributed in most populations. Okay, and then another assumption is Levine's test. Now, here in this write-up on the slide, it's showing you writing a whole sentence about normality and a whole sentence about Levine's test, and I want you to practice that in this class, but I have never seen those written out in a manuscript. Usually because it is assumed if you're doing a t-test, you already checked these things and you would not proceed if they failed. But just know when you read an article, you might not see them specifically taking up 2 sentences to say that they tested these things. But in your dissertation, your committee would want to see it. If not in the main part of your manuscript, in an appendix. So testing Levine's test here. So additionally, the assumption of homogeneity of variance was tested and satisfied via Levine's test. And then the data is Levine's test is here at the end. Now this is not the same numbers that are above. There we go. And then the independent samples t-test did not find a statistically significant effect. And then here we have our t with 8 degrees of freedom equaling the value. Oh, you know why this doesn't match? There was slightly different data were entered in his R versus when I fixed it in mine. There. So there was no evidence that the drug reduces depression. Now, when you guys eyeballed it, and when you looked at the averages, both times you said, yeah, the drug does something. But this t-test, what does it say? No evidence that it makes a difference. Anyone have any ideas on why that might be the case?
I'm wondering if it's maybe really close to a confidence interval, like just barely outside.
Let's look at the middle of this output. Here's the confidence interval from -10 to +1.2. 0 means no difference. Is 0 in that confidence interval? Is 0 inside of it? Yeah, because we go from a negative number to a positive number, so 0 is inside of there. How close is 0 to either one of those edges of the confidence interval? It's close to 1, right? 1 is close to 0. So if you think of the confidence interval, think of drawing a number line, and you're going to go from -10 to 1. Where's 0? 0 is close to 1. Now, how big was our sample size here? Little, right? let's see, what if we, now I'm kind of faking it out here. What if we had done twice as many people? What if we've done 10 and 10? And to make it easy on myself, I'm going to replicate the data. What if we, and if this would never happen. Come on. I'm getting this little clock thing here. This usually means something else is hanging up. Oh, down here, something's hanging up. Okay, so I duplicated the data. So now we have sample sizes 10 and 10. See, our sample sizes are 10 and 10. The averages are the same. What about the standard deviations? They're about the same. We plot it, you get about the same. Levine's test, did it change? Yes, but it's still no violations found. Now look at our t-test. Bigger samples have more power to find statistical significance. We are looking at the averages with the spreads in mind and the sample sizes in mind. The t-test, let's go back to the formulas for the t-test. Bring this formula sheet over here. What is involved in doing this t-test? What numbers are there? On the top of the, now in this formula sheet, on top, it has a D, a capital D with a bar on it. That capital D with the bar on it stands for the difference. Let's see, can I slide over here? Right there, see the capital D with the bar on it is the bar is average, so it's the average difference or the difference in the averages. So this is the averages, that goes on top. But when we're doing a t-test, what goes on the bottom to calculate t? What numbers go in there? Your sample standard deviations, and what else? Your little n's, your sample sizes. So and this is kind of getting into the next chapter, the power of a test or its ability to declare statistical significance depends on your spreads, your samples, and your sample sizes, n's. Both of those are part of doing the test. So this time we found with the original data with only 5 and 5, even though there was a numerical difference, that the averages were different numbers, there was not enough evidence to declare statistical significance. So we kind of put the cart before the horse. We did a test, but let's go over what the assumptions of that test are. So number one, this looks familiar. Independent, well, the random samples looks familiar, but now that we have 2 samples, they have to be independent random samples. There is no way to test this statistically. You want to plan as well as you can that you can have the most random, most representative, most independent samples possible. The second assumption is that you have normally distributed variables. How do we test that? We can do the plots, we can do Shapiro-Wilks, we can calculate skewness and kurtosis. This is probably the least important of the 3 assumptions because if you have a big enough sample size, or then the central limit theorem will take over. 5 and 5, that's not big enough, but hopefully you have more than 5 and 5 in your own work. The last assumption is very important, the homogeneity of variance assumption. If we do Levine's test and the null hypothesis is that nothing's going on, that they're the same variance, if that's violated, we can do the Welch's alternative, that separate variances t-test. So it's not the end of the road, there is an option for that. So random, assumption number 1 is that we had independent samples. The best way to guarantee an independent sample is to do random assignment. That you use some kind of flipping a coin, rolling a dice, random number generator to decide who goes in which group. It does not ensure that the groups will be equally broken down, but they'll be randomly assigned controls for all possible confounders. Now, sometimes we can't randomly assign. The participants are either self-selecting or naturally forming groups. If we're looking at gender differences, male and female, we can't randomize that. If we're looking at whether or not someone is or is not a veteran, we can't randomize that. It just is pre-existing, so it's a non-experimental situation. We can still use those groups. The problem is we can't say cause and effect. We can just say things are associated. So in the example we just did, we randomly assigned to take the drug or the placebo. So if those groups are different, the difference has to come from the pills. If we were looking at depression over 6 months and we had veterans and non-veterans, could we say it's due to their veteran status? Maybe the veteran people have different experiences. Maybe they're older. Maybe the way that we were able to find them what meant that they were enrolled in a certain program. You have to be alert to possible confounding factors if you are not randomizing the experiment. If you have equal size groups, your violations to assumptions hurt less. In that, even if you don't have exactly the same spread, if your groups are the same size, it's not as problematic. Always equal size groups is more powerful and more resilient to violations of assumptions. This is why when we plan studies, we always want to plan for our groups to be the same size. Now, even if you plan to enroll groups of the same size, what happens during a study with human people? People move away. They decide they don't want to participate anymore. We have dropout and attrition, but you want to always try to get equal groups. If you have unequal groups and you have your violations to homogeneity of variance, violations to normality, those things can really hurt the accuracy of your results. Now, if you have one violation, that hurts a little bit, but if you have two, it's more than doubly as bad. If you are violating all the normality assumptions, some things are not normally distributed. They just aren't. Some things are skewed, like number of tattoos on Utah State's campus per person. That's not bad. It just means you can't do a t-test. And there are other options for tests that we're not going to learn in this class. The Mann-Whitney U is one of those, and it looks at the difference in the medians instead of the difference in the means. Okay, so we're still going to be able to do confidence intervals when we have two groups, but the confidence interval is not for one group, it's not for the other group, it's for the difference between the groups. So if we look back at this test that we did, this group had the drug group had an average of 2.8, the placebo group had an average of 7.8. What's the capital D bar? Capital D bar is the difference in the averages. Yeah, Melissa? 5? Oh, you're putting 5 fingers. Yeah, 5. The capital D bar, the observed difference in the two groups is 5. But in the populations, is it exactly 5? We're not sure. What's our confidence interval? Well, here it's between 1.5 and 8.5. Now, they're both negative, but we could flip it the order of subtraction around and they'd be both positive. So this says that the drug, how much does the drug reduce the depression scores? It's 5 lower, but it might have only been 1.5 lower in the population, or it might have been 8.5 lower in the population. 5 is our best guess, but if we really want to be sure, we can be 95% sure it's somewhere in between 1.5 to 8.5 points lower. That gives us a margin of error range where we can be more sure. Our point estimate of 5 is our best guess, though. Come on, come to the front. That doesn't want to come to the front. Oh, it's over there. Here's another example. We have an industrial psychologist working with people working in industry, investigating the effect of different types of motivation on the performance of simulated clerical tasks. What would be a clerical task? Any ideas?
And answering phones, or
Answering phones, maybe
What-
filing a folder, maybe addressing an envelope, maybe bringing up a receipt. There's some kind of clerical task that they're looking at. So they have 10 participants. Think of yourself in this study. So 10% participants are put in the individual motivation. They're randomly assigned to individual motivation. And they get told that they're going to be rewarded according to how many of these tasks they get done in a certain allotment of time. The other 12 participants are told that they have group motivation, and they're told that they are going to be rewarded according to the average that their group gets done. Not how many they do, but how much the group averages. And then the time goes on and they measure how many of these tasks these people do. Now, these two groups are size 12 and size 10. My guess is they probably had 15 in each group and some dropped out, and this is just what they had at the end. But so we have two groups, 10 and 12 are the two group sizes. Those are our little n's. So here's in the individual group, here's how much they got done. 11, 17, 14, 12, 11, 15, 13, 12, 15, 16. And then underneath here are the number of tasks completed for those that were told that they were going to get paid versus based on the group's average. Eyeball method, which one got more done?
the
Individual.
Eyeball test, looking at these 10 and 12 numbers, would say the individual. Here I put it into R and done a little little table 1. The individually motivated people got an average of 13.6 done. The people that were going to be told based on the group's progress only finished 9.8 on average. Eyeball test says individually, people are get more done with individual motivation versus group motivation. I don't know if this is real data. This might be made up, so don't read too much into it. That's the description. This is descriptive. What would be our capital D bar, the actual observed difference between the two?
1.8.
So 1.8. We'd take 13.6.
Oh, I was looking at the other one.
9.8. Yeah. 1.8 is the difference in the spreads. Yeah. But the means, what's the difference in the means?
3.8?
3.8. Capital D bar, we observed 3.8. But our statistical significance will be based on that idea of a margin of error. Even though this sample saw individuals get more done, are we sure that we would say that if we did this on a larger scale, individuals would for sure get more done? So here's the plot of the data. Does the plot eyeball? Anyone notice anything about the plot? Those center bars are what measurement in the middle of the box? What does that represent? Is that the mean?
No.
No, what's the center of a box plot?
The median.
The
Median.
median. If we look at these two box plots, how do they compare? The individual motivating and the group motivating. How do they compare in terms of their center? The individual has a higher center. How do they compare in terms of their spread?
The group has a much larger spread.
There's a lot more spread in the group. Do you think that we're going to violate homogeneous variance or meet the assumption of homogeneous variance?
violate it.
It looks like we might violate it. Let's do Levine's test to make sure. So here I've said Levine's test. Here is Levine's test results. What do the results of Levine's test tell us? They put a little asterisk next to it. It's less than 0.05. So that says we reject the null assumption of nothing going on. So this is evidence of violations of assumption of homogeneity of variance. So should we do a pooled variance t-test or the separate variance Welch's t-test?
The separate?
The separate. So we say var dot equals is false, and it does the Welch's. And we know that because if we look at our degrees of freedom, they are a decimal number. What was the smaller of the two sample sizes? What were the two sample sizes? Let's go back. The sample sizes were 10 and 12. So the smaller number that it could be would be 10 minus 1 is 9. The biggest the degrees of freedom could be would be combined sample size minus 2. 10 plus 12, 22 minus 2 is 20. So the degrees of freedom for our Welch's test is going to be between 9 and 20. Is it? Yeah, it's a decimal number between 9 and 20. If I was doing this by hand, I would have said 9 degrees of freedom to be conservative. If you have to ever look up a degrees of freedom in the t-table and it's a decimal number, always round down to be conservative. But if you round up, you should get the same answer in the answer key on Canvas, because I've learned how to do a range. Okay, so we are going to do, because of Levine's test, finding significant violations of homogeneity of variance, we decide to do a Welch's t-test. And what are the results of this t-test? Is there evidence that the groups differ in terms of the average? What's our p-value? 0.008. So this is evidence that our groups differ. But when we write our conclusion, we need to say which direction they differ in. And so if we look at the very bottom, they have it, our averages reported for us. So the first group is the individual motivation. Their average was higher at 13.9, and group 2 was the group motivation, and their average was lower at 9 3/4. 9 3/4. Okay. So when we write this up, we want to include, now this is a really, really thorough write-up. It has descriptive information about the two groups, their sample size, average, and standard deviation. It tells which test we're going to do, independence group t-test. It tells about the assumption of normality and homogeneity of variance. And notice here it says up here that it's at the onset, it says it's going to do an independent samples t-test. And it's after the reporting of the Levine's test of homogeneity of variance that it states that a separate variance t-test was used instead of the pooled variance t-test. So the conclusion here, individual motivation does result in a higher average. How much higher? 3.85. Where did 3.85 come from? From subtracting these two averages. And then here's the confidence interval to go with it. Okay. Separate variance versus pooled variance t-test, comparing two groups. We ready for a break? Let's have a 10-minute break. If you have questions for me, come back faster than that. But if not, let's have a full 10-minute break. Okay. See you back here in 10 minutes.
Hey, Sarah.
Yeah.
So on my homework 5, some of them I tried 3 times because I was trying to kind of check to see, because like on the one I had it right, the p-value wasn't negative, but then I was trying different things to see if I could figure out what was going on. So I ended up with 3 tries with the wrong one.
Mm-hmm.
Do I just get like those wrong, or is there a way they could be reset?
The only way for me to reset them is to reset and have you start all over.
Oh, never mind. I'll just take, I
can't
mean,
give-
it happened on like 3 answers, but that's fine.
Yeah, I don't think that it's going to make a huge difference on your grade. But definitely send me an email. And I know you sent me one before on it, but send me another one saying, reminding me about that, and I'll make a note of it.
Okay.
Yeah, if I say that you get 3 tries, I cannot change that again. The only thing I could do is give you an extra attempt, but you'd have to start everything all over again.
Oh yeah, it's not worth it. I'll just.
Yeah, I
check
didn't
the
think you'd want to do that.
And as far as the homework 6 problems, I sent you another email about those.
Okay. Yeah, the 6 should be right. I spent an extra 2 hours going over the answers for 6, so they should be all right. There was 1 or 2 things, but if you sent me an email, I'll look at it. I haven't checked my
Thank you.
email since I started clients this morning, but I will
Okay.
tonight. Okay.
Thank you. I appreciate that.
Okay.
That way I know where did I make the mistakes so that I don't make them again.
Yes. Yes.
I was wondering on like homework 3A, I was telling the direction, but the correct answer was just that it was different. I mean,
If it's not significant, then it's no difference. You only say the direction if there is a difference.
Well, there was a difference, but so I put better because there was a difference, but it said instead of better, I should have selected they were just different.
Send me an email on that one. Let me check. I thought I'd gotten those all fixed, but I'll definitely check it if you think it's still wrong.
Well, I don't know. That's what it happened to me on 2 of them. And so I just thought I must not understand something.
Yeah, send it to me and I'll double check it for you.
Okay, thank you.
Hey, Sarah.
Yeah.
I am looking at my homework 6 and my little button that lets me check my answer or try it again is missing.
For
Problem.
everything?
No. For problem 6A, number 5, letter A.
Okay, would you send me an email on that and I'll get that fixed?
Oh, okay.
Yeah. And
Let's
I
see.
tried so hard to get those answers right on that on 6. I really.
I know, it's totally cool. You're awesome. I just didn't know. I couldn't fix it because the
Yes.
test was gone.
Yeah, I
just
have this.
code.
I wish I could set it for the whole assignment. I have to re-say 3 tries, give partial credit on every single question. And so once in a while I miss one.
Yeah, and I appreciate that you set it up this way.
I wish that it would just automatically do it.
I know. Why it should. Like, tell Neil, hey dude, you need to
I know. I was so excited he told me about it though, because I think it's going to be a game changer.
This is a game changer. I've already talked to several people in our department about the atomic assessments. I'm like, this has got to happen. We've got to move to this.
Well, you can do figures that you label, and you can do all kinds of plotting types, and so it's really flexible.
I mean, it's more interactive than anything else. It's super cool. So thank you for that. Sorry.
The only downside is you can't use it with Procterio. Canvas has regular, what they're calling classic quizzes, and now they've introduced the new quizzes.
What Procterio has?
Canvas has. Canvas has classic quizzes, new quizzes, and now there's atomic assessment. But with Procterio, you can only use the old classic Canvas quizzes. Which is kind of a bummer. And I know that because Neil told me that.
Gotcha. And you know how I told you about the mean on that one question, 6B number 8? Still marked it wrong again.
Yeah, send it to me again.
Okay.
The answers, you can mark what kind of answer it is. If it's symbolic, literal, value, and there's some other things, like if you want them to, if it's like factoring or something like that. And literal, it has to be exactly the same. If I make it to value, that's when it will ignore trailing zeros, and I can add a plus or minus amount. Okay, because when we report our sample statistics, it's okay to go to 2 decimals, right? It should be 4. Okay. Yeah, and I on one of them, and I need to make sure, when you said that, there was one that was 0.25, I think. No, there was one of them that you put, and I had it as a literal, and it was, I had put it in as 4 decimal places. The one you had was the one that was a t-score, a t-value, t-critical value. You'd put 2 decimal places because the third was a 0, but then the assignment wanted all 3. Anyway, I have to make sure it's marked right. Gotcha. Okay, so sample statistics, we want 4, even if it's to 0. So if it's like 5.38, type 5.3800. Yeah, the reason that I usually do that for the sample statistics is because they're used in the formulas, and if you round them off to 2 decimal places or 1, and then you use them in the formula, it starts getting rounding error compounding. Oh yeah, for sure. Okay, cool. Okay. Are we all back? I changed these slides so they're going to be white background and not that terrible background. That'll help that one. I'll keep tidying that one up. All right, pooled variance, separate variance, Levine's test, all kinds of new fun stuff. Other than that, there's a lot of recycling of old ideas, right? The idea of a t-test, a confidence interval, p-values, those should be recycled ideas, which is always great. Okay. Oh, we're not doing multiple imputations. We need a new slideshow. Let's go back to your class page. Chapter 7, no, 8. This one's a PowerPoint. No, 7 and 8 are old PowerPoints. They're not the HTML. Maybe if I get Now, we'll see if I can get homework assignments 7 and 8 up first. I'll get those HTML. Okay. Here we go. Power and effect size. This is one of my favorite chapters. Let's see how.
This was really rough for me.
Was it really rough for you? Let's see. I want to start with this slide. So there's kind of this chicken and egg problem with research, is when you want to do a study, you don't know what the average is, you don't know what the standard deviation is for, you're usually looking at multiple groups, whether it's a pre-test, post-test, or it's a treatment control, or it's diagnosis A versus diagnosis B. You usually have multiple groups, but even at that, you don't know the means and standard deviations. You don't. That's why you're doing the research. But the first thing you need to decide is, how big does your sample size need to be so that you can go gather data, right? Because you've got to write a proposal, and it has to be justified, whether that's to your committee and or IRB and or a funding agency. You have to decide how big your sample size needs to be and justify bugging those people and putting them at risk or taking their time and energy away to do your research. So you need to know what sample size you should have. Well, to decide on what sample size you should get, you need to do a power analysis, and power analysis is based on how big you think the effect size might be, or what an interesting effect size would be, which is based on what the means and standard deviations are, which you don't have. That's why you want to do the research, but you can't do the research until you decide on how big the sample size should be. So it's kind of like this cycle. So if you start studying something new and you have no clue about how big of an effects or what the means and standard deviations are going to be, you just have to kind of jump in and do a pilot study where you just gather some data, as much as is feasible with your budget and time constraints, to get proof of concept going, to get some estimate. If you're writing up a proposal, which all of you are doing for your dissertation, but also you'll probably do for all kinds of other research if you go into research, you always have to have a section that's based on power analysis or sample size estimation. So in this blue circle, we have calculated before you collect your data. So before you go collect your data, you need to have the power, the p-value, the effect size, and the test statistic cutoff that you're going to use. Then when you observe your data, we can also calculate power, p-value, effect size, and the test statistic as well. And it's kind of the cycle of where you get started. So let's go with the definition of power. Power is the probability of correctly rejecting a false null hypothesis. So when you do the scientific method, you have an idea that there is some effect. There's something going on. That's why you're studying it, right? Whatever it is you're studying. So we set up the null hypothesis as the straw man to knock down. We want to reject the null hypothesis usually, because the null hypothesis is usually that nothing's going on. So the null hypothesis might be the drug does nothing, the placebo and drug group are the same. But really the hypothesis we're interested in, or that we think is the case, is that the drug is useful. Now, if we have COVID patients and we want a drug that's going to help them with their respiratory disease, if we give no one the drug, some of them are going to get better. But we want to know, if we give other people drugs, will more get better than would without it? So that's a comparison. So the power is the probability, so it's like a chance, of correctly rejecting the null hypothesis. So if the drug really works, we want to be sure to show that it works. So power is the chance that we would correctly say, this drug does great, when it really does great. It's the opposite kind of that type 1 error, which is the false positive. This is like correctly saying it's a positive. Now, This diagram is one that's used a lot, and it's not my favorite representation, but it's a way to show the different conclusions you can draw. So on the side of this plot, it says the true state of nature. So this is the truth. This is what we don't know when we're a researcher. But if we were God, we would know the truth. Either our null hypothesis is true or the null hypothesis is false. There is a truth out there. We don't know that. We think we might, but we want to establish it. The conclusion we draw after we gather our data and crunch our numbers could either be to accept that hypothesis or reject it. Now, if the hypothesis is true and we accept it, that's good news. If the hypothesis is false and we reject it, that's also good news. But there are two types of errors we can make. Remember, there's the false positive and a false negative. And we use alpha for the type 1 error rate, and we use beta for the false negative rate. And so usually the alpha, the false negative, that's the false positive. This is the one we're most concerned with. So we set alpha to be 0.05. Now I said that there is some kind of, if you make alpha teeny, 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 tiny, it will inflate your type 1 error rate. And if you make your power super, super high, it will has a tendency to have an effect on your alpha rate. There is kind of a, not direct tug of war, but there is a relationship between those two that is a little bit complex. But in general, power is 1 minus beta. So beta is the type 2 error rate. And so power is 1 minus it. 1 minus because 100%. We're talking not in percents here, but in proportions, so decimal numbers. So just like we set alpha to be 0.05 in most cases, because that's usually small enough, there is a beta, a 1 minus beta of 80% is the most common power kind of line that most funding agencies like the National Institute of Health and the National Institute of Education, a lot of these funding agencies require you to have 80% power, meaning you have a sample size that's big enough to detect true effects 80% of the time. Now, I will say that this is changing. This is a little bit in flux. With the movement towards registered reports, with Dave Bolton last year, we filled out a registered report and their criteria was 90% power. And I've heard of some being 85. So anytime you're going to write a grant, somewhere in the call, there will be some information about the power. And if they don't say otherwise, then 80% is what we usually go with for most major funding agencies.
So, hey, Sarah, wait. Go back to that cool, yeah, yep. So on the bottom right-hand side where it says good conclusion, is that power? That's rejecting when it's in fact false. So would that be the power of your test there, or does that not, am I not thinking that right?
Probably correctly rejecting a false null hypothesis, correctly rejecting. One minus beta. Yeah. Now, the way this is set up, so it's a perfect 4x4 grid. But in real life, are half of hypotheses true and half false? No. And do we half the time accept and half the time reject? No. So this arrangement, like that the squares are all the same size other than those red ones, is kind of misleading. So you could have someone who, and this was some bonus material that I cut out of the chapter 6 assignment that I used to do the advanced material. If you read through the advanced material, if you are a researcher and you have done 10 studies and all of them you were able to reject the null, is something wrong? If in 10 studies you said reject the null in all of them, is something questionable about your research? What if you only pick things like eating carrots is more healthy than not eating carrots? What if you picked going to school helps children read more than not going to school? What if you picked reading 100 books is better than reading no books? You can pick your hypotheses that are pretty much slam dunks. And so it's not 50-50 to begin with, which is why I don't like this diagram. It's a good call. Okay. So where do we want to go next? Okay. Cohen said, I have learned and taught that the primary product of research inquiry is one or more measures of effect size, not the p-value. This is very, very important. Up till now, we've focused a lot on the p-value. Is there a statistically significant effect? Is the difference statistically significant? Is that p-value less than 0.05? But Cohen's saying a little more. Now, this is not Barry Cohen of our textbook. This is Cohen of Cohen's D. I forget what his first name was. And this other guy said, all social scientists, as social scientists move gradually away from reliance on a single study and obsession with null hypothesis testing, effect size measures will become more and more popular. Now, if you haven't heard of it, there is a crisis going on in social science. Social scientists have been in love with hypothesis testing, which are a great strategy, but they have been very recipe-ish about p-values for a long, long time. And not any one person, it's just in general, most social science research psychologists have generally fallen into this way of thinking, which there's nothing wrong with hypothesis testing. However, the p-value doesn't tell you everything. The p-value is very much an effect of the sample size. Remember when we saw to calculate t, on the bottom of the t statistic, there's a bunch of stuff going on with the sample size and the standard deviation. The bigger your sample size is, the more powerful your test. The smaller your sample size, the weaker your test, by virtue of how much data you're able to gather, how well you're able to say the population, what the population would be like based on the sample. So we kind of introduced that there's this other idea about how big of an effect there is. So even if we say that we have statistically significant there's effect, that doesn't tell us how big of an effect and whether that has any practical implication. And that's the idea of effect size. It's how big of an effect does something have. So we might show that a new kind of teaching helps children read more, but only helps them read one more word per second. So they're now reading 61 words per second instead of 60. Is that really that big of a deal that we should get excited and change the national curriculum? Probably not. So the effect size is a way to measure how different or how big of a difference something makes. Now there are different kinds or different flavors of effect size. Cohen's D is the one that we use when we have two independent groups. So this will look, here's the formula for Cohen's D. So Cohen's D, the general format that Cohen suggested is you take your two groups, you subtract your average, you'll get a difference. And then to standardize that, we're going to divide by the pooled standard deviation. Now, if you have the averages and the pooled standard deviation, you can calculate it. And this crisis of p-value reliance is, there was a whole task force on p-values in social sciences, the APA made, and one of their conclusions is every time we document a statistically significant effect, we should also include the estimate for how big of an effect there is, so that we can make comparisons study to study about the sizes of these effects. And the way he said we should standardize is we should divide by the pooled standard deviation. It's very simple if you have two groups that meet homogeneous variance. The simplest case, if you have exactly two groups and you have homogeneous variance, you take the two group averages, subtract the group averages, and divide by the standard deviation. This will tell you how many standard deviations the averages differ by. Now, a lot of past research, and even some today, is being published without Cohen's d. And if you do the algebra math that you guys care so much about, no you don't, you can get this other formula. So if you are reading somebody else's article and they did not put an effect size in terms of Cohen's d, but they do report the sample sizes and the t statistic, you can do this math and come up with the same number you would as if you had had the averages and the pooled standard deviation. Pooled standard deviation is very rarely reported in two sample reports that I've seen. Now, the Cohen's d is a really good effect size measure when we're comparing the averages of two groups. There is another more general effect size called Eta Squared, and we're going to use this one a lot with our ANOVAs because it can generalize to more than two groups. If you have two groups, Eta Squared is the correlation between the continuous variable and the categorical two-group variable when you score it 0, 1. It's often called the point biserial correlation. Just putting that up there for future reference, not that we're going to need to worry about that so much now. Right now, for our two-group t-tests, we're going to use this Cohen's d measure. And Cohen, when he suggested this, standardized the number of standard deviations the means differ by, he came up with some cutoffs. Now, these cutoffs are not a recipe. They're not a line in the sand. I really loathe that people rely on these without thinking about what they mean. So how big of a difference has real life implication is not solely based on these cutoffs. It also depends on what you're studying and what population you're studying on. So finding 1 word per minute more for students that have an intellectual disability, that might be more meaningful than a 1 word increase for the general population. So just a Cohen's d effect measure gives us some common framework to compare effect sizes, but it's not the be all end all. And some things naturally have more noise and more things involved, and other things are more simple and easier to find effects. But these are the general cutoffs for saying something has a small effect, a moderate effect, or a large effect. Generally speaking, if your Cohen's d comes out to be the number 1 or bigger, about a 1.0, that means the two group averages are 1 standard deviation apart. If your Cohen's d is 0.5, that's the moderate middle one here, that means your two group averages are a half a standard deviation apart. And so this is some common language we can use. So this Eta Squared is more of an association between the grouping variable and the continuous dependent variable. What's nice about an Eta Squared is that it's always between 0 and 1. Cohen's d has no ceiling. You could have a Cohen's d of 500. Probably not, but you could. There is no upper end on that. But Eta Squared is always like a percentage between 0 and 1, a proportion between 0 and 1. With two groups, the results are the same for Eta Squared as it is for the point biserial correlation. So the way I think of power is a recipe. And there are, if we said a recipe for soup, how many different recipes for soup are there? A lot. So this is an important thing to know. Your recipe for power depends on what analysis you're going to run. Power analysis for 1 sample t-test is different than power analysis for 2 sample t-test, is different for a one-way ANOVA, is different for a logistic regression. So I a lot of times have people come to me for consultation to say, I need to run a power analysis. And my first question back is, what analysis do you plan to run? Because you've got to have, that's like your formula or your recipe. Is if you don't know if you're doing a 1-sample t-test or a 4-group ANOVA, you can't do your power analysis. So we need to have, our recipe is the type of analysis we're doing. The good news is all of those recipes have the same ingredients. And those are the ones that are listed on this slide. Sample size, effect size, alpha, and directionality. Those are the components or the ingredients for every power analysis. Now let's start with number 3, alpha. We are familiar with alpha. What alpha are we going to use without anything else to go on? 0.05. Okay, we can always answer that one pretty easy. The power, we almost always say power is 80% when we're doing a power analysis. The sample size, that's usually the thing we want to know. Now with algebra, we all have taken algebra at some point in our life, whether we liked it or not. And with algebra, we'd have equations. Did you ever have to solve an equation for x? If you have it, what do you do if you have an equation with lots of letters in it and you need to solve for x? You have to plug numbers in for everything else but x and then get x alone. Have you guys done that? Maybe many years ago? We're going to do the same thing with the power analysis. You need to plug in all of these components, or if you can plug in everything but one thing, you can solve for the one missing thing. Usually we want to solve for sample size by plugging in values for effect size, alpha, and directionality. So, oh my gosh, it's gonna come. I'm gonna sneeze. Okay, so the last one down here, directionality. How many tails are we gonna do? 1 tail or 2 tail? 2, unless we have good reason to do 1. So let's see, I think the next slide's an example. The book has this power table in the back of it. I think it's table 3. Let's not use that, shall we? Is anyone uncomfortable with not using this? Kimberly, have you ever seen this non-centrality table? I'd never seen this table in my life till I started teaching out of this textbook, which tells you how much it's used in real life. We're gonna throw this table out. How's that? There are some formulas that we can use, but let's get right to examples. Let's go to G-Power. So G-Power is this nice little piece of software that's really, really handy. And it is used all the time. And anytime you're gonna write a proposal, like your dissertation or a grant, if you say you're using G-Power, people will know what you mean. It's that well known. It's the most common power analysis software. So can you guys see my screen? Is it really tiny? I have not found a way to make this bigger on my screen. It's like set. Now, who has Macs? Okay, so G-Power works great on a Mac, but this is the one thing I found. This window on a Mac, sometimes your screen resolution will make it so this window is like down low, and so you won't be able to see this calculate button. If you cannot see and click on this calculate button on, and this happens a lot on the MacBooks, you need to change your screen resolution so it like zooms out, so you have a higher resolution, so it makes your window smaller so you can get to this calculate button. This is the one issue that I've seen more than anything with G-Power. It's just changing your screen resolution so you can get to that button. Okay, there's a lot of different things going on this screen, right? We are going to ignore the top part and we're going to go right to the middle part. So with power analysis in G-Power, we've got to get these 3 center drop-down menus selected first before we can put any numbers in. So the first drop-down says test family. Now, G-Power cannot do all types of statistical analyses, but it can do some really common ones. What are the ones that we know so far on this list? T, there's a Z down there, but we're gonna go with the t-test because we now know 1 sample t-test and 2 sample t-tests. So we're gonna do t-test. I think that's the default. I believe when you go in here, the default for the statistical test will say correlation point by serial model. Is that what yours says? We're not going to do that. If you click on that drop down, you get a lot of other options. Look at the center ones. There's 3 that say means difference. So the one that I have highlighted is means different from a constant. That's a 1 sample t-test. We've learned how to do those, right? And then right above that, it says means difference between 2 independent groups. 2 groups. That's what we learned how to do today. And then what's right above that? Difference between 2 dependent means or matched pairs. We'll come back to that later. So these 3 are the ones we're going to do. Now, notice what's under that. There's the Wilcoxon sign test and the Mann-Whitney-U test. Those are some other non-parametric tests that we're not doing right now. Let's go to that middle one, the very middle one. Difference between 2 independent means. That's what we were working with today. So let's go to that center one. Okay, so there's the 3 drop downs. We did test family, statistical test. Now we have to do type of power. Now I said there's all those ingredients in a power analysis. And as long as you plug in all but one element, you can solve for the one missing variable. So each of these 5 options are solving for a different ingredient in the power analysis. The very top one is called a priori. This is where we compute the required sample size if we give it alpha, power, and effect size. This is the most common use of G-power, is before you do your study, a priori, you want to decide how big your sample should be. Now, there are other times when you might be locked into your data because you're already using a pre-existing data set, or there might be limitations due to budget or time or some other constraints. In those cases, you know the sample size you're going to have, so you can solve for other things like the effect size and alpha. But we're going to go with this top one, a priori. Okay, so we're going to do a power analysis for the difference between 2 independent means to decide on the sample size we need before we do our study. That's the middle group. Now notice this top part is still blank. It'll be blank till the end. It'll make a plot there eventually. Now if we look at the bottom section, there's 2 sides. On the left side, it says inputs, and on the right side, it says outputs. That very first thing on the output says non-centrality parameter, and it has that delta symbol. That's what that table in the back of the book's for, that we're not going to worry about the table, okay? So inputs, let's look at these inputs. What's the very first input? How many tails? How many tails are we going to do? 2. What was the default that it went to automatically? I do not know why they set the default to 1, because we almost always do 2. So you'll have to change that. Let's skip effect size for the moment. Then there's alpha. By default, what does it say alpha is? 0.05. We're good with that. The next thing down, power, 1 minus beta. By default, it sets power to 95. I have never seen anyone require 95% power. We're going to change that to 80. And then the last thing there, look what it says. It says allocation ratio, N1, N2. Now these are the sample sizes. Now what did I declare at you today? The most powerful, best studies are one in which the sample sizes are the same as each other. It's more powerful if the sample sizes are the same size. It's called balance in your sample size. And if we balance it, that's an allocation ratio of 1 to 1. 1 for you, 1 for me. 1 for you, 1 for me. So 1 to 1, what do you get when you divide 1 divided by 1? 1. So that's this allocation ratio is 1. That's the most powerful. Now there are times when, because of the stuff we're dealing with, we know we're going to get 2 normal kids for every 1 at-risk kid. And that's when we might want to change that allocation ratio to 2. 2 to 1, or if you divide the other way, 1 divided by 2, you get a half. You can enter that in. But almost always we want to plan for equal group sizes, knowing that due to attrition, we might not end up that way. Okay, what was the only thing we didn't fill out that we skipped? The last ingredient. We skipped one of them. Effect
Effect size.
size. And notice what does it say? Effect size D. That's Cohen's D. That's how many standard deviations apart our group averages are either expected to be or the minimally important, or what would be the smallest effect size that would be important to document or have important meaning. In reading, if I was doing studying on reading in words per minute, how many standard deviations of a difference would it have to make to be of practical importance? That's the question. Now, if you have nothing else to go on, you can use Cohen's cutoffs. And it's easier on PC than Mac to do this. But if you hover your mouse over that Cohen's D spot, sometimes it's kind of temperamental. It'll bring up, there we go, I got mine to do it, the little cutoffs. So it will remind you, 0.2, Cohen's D of 0.2 is considered small, around a 0.5 is medium, and around 0.8 is large. What does it default to? 0.5, which is medium, a half a standard deviation. Let's leave it there. We've got all of our inputs, all of our ingredients put in. Now if we push calculate at the very, very bottom, it will calculate the sample size we need. How big of a sample is required to be 80% powered to detect a 0.5 Cohen's D effect size at alpha 0.05, at a 0.05 significance level?
64.
64 in each group for a total of 128. Now this is the sample size we need with complete data. If this is the sample size that G-Power says you need complete data on, what are you going to go try to enroll? Just 128? What happens if you enroll just 128?
Some are going to drop out.
Some are going to drop out. Do you know how many are going to drop out? No. So part of your power analysis justification section in your proposal is something like, in G-Power, a 2-sample t-test for independent groups, to achieve 80% power at a 0.05 significance level, we need a sample size of combined sample size of 128, assuming equal group size and an effect size of 0.5, Cohen's D equals 0.05. And then you would follow it up. We anticipate a completion rate of 80%, or we anticipate an attrition rate of 15%. Thus, we are going to try to enroll 150 or something like that. How do you know? You're going to have to take a guess at your attrition or dropout rate. It needs to be based on as much past experience as you can, either your mentor or prior publications, or it is very dependent on what you're asking your participants to do and who your participants are. If you're asking elementary schoolers to do some simple tasks that you can have their classroom teacher helping with, you might have a higher completion rate. If you're sending out surveys by email, good luck. You're going to have a very low completion rate. So depends a lot on what you're doing. Okay, so let's see, we said for an effect size of 0.5, we need 128. What do you think is going to happen if I make this effect size smaller? A smaller effect size. What smaller effect size, so your averages are going to be closer together. What do you think that's going to do to our required sample size? I'm seeing some of this and I'm seeing some of this. Shall we see? I'm going to make the sample size difference, the effect size small, and I'm going to push calculate. Whoa, what happened? To detect a small difference, we need big groups. Let's see, let's try one more time. Let's do a great big effect size. Let's a huge effect size, an effect size of 1.0, 1.5 even. A 1.5 big effect size. What's going to happen to our sample needs? Whoa, only 9 in each group. If our groups are very different, we only need a few in each group to be able to say. But if our groups are very close to the same, we need a big sample so we can be able to really tell if that's random chance or a true difference. Is it the same as you expected or different?
Different.
Different. Some of these things in statistics are different than you would expect on first glance. If a drug only makes a little difference, we know there's fluctuation in samples, right? Remember our sample data we saw before only had 5 and 5? In the group that had 5, one person was 11. Was that an outlier or not? It's hard to tell with small samples. If you have small samples and you take and a small difference, they might overlap a little bit. Now, if you push, this is interesting, on this G power at the very, very top, so it's drawn this picture once we saw calculate. I'm going to put this back to a moderate effect size of 0.5. If you push the other tab at the top, this gives you everything. Now, this is a really nice thing to put in your appendix to your proposal for your dissertation or for a grant or anything like that. And you can pretty much just copy this into an appendix and paste it. Hold on a second, we're having a issue at home, a problem, emergency. I have the link to the group piano lesson. Okay, there we go. All right. So this tells you everything you need to know. It tells you that you're doing a t-test for the difference in two independent group means. So that's what we chose. The type of analysis, a priori. We're computing the needed sample size. It tells all the inputs and all the outputs. And you can print this, save this, and it keeps your history. So here's the history of everything with timestamps, date and timestamps. You can clear it and then run it again. So you can just copy this and paste it into your appendix on your power analysis. So what is D? Cohen's D. D is the number of standard deviations that separate the two population means. Now, the definition of Cohen's D, he said in terms of population means. Now, how do we calculate it? It's supposed to be the formula for Cohen's D. Let's see here, where's Cohen's D? Now this formula, what is on the top of that fraction? They're X bars. Where do X bars come from? The population? No, they come from the sample. So Cohen's D is supposed to be about the populations, and we estimate it by plugging in sample data. That's not a perfect estimation. Now I'm coming back to that formula sheet. Oh, I've got it open over there too. Can't see you guys. There we go. Okay, so on this first page of the formula sheet is all the t-test stuff. If you turn it over or you print it out, the next page at the top has effect size information. So in here's all the formulas. Now, will you have this paper with you for the test? Absolutely. If you want to print it out, I will put the important bits on the test anyway. But here is Cohen's D formula right here. See, it says two groups. Cohen's D, notice in the Cohen's D real formula, what is on the top? Not X bars, but mu's. Mu1, the population one's average. Mu2, the second population, the other population's average. And what's on the bottom? Sigma, the pool standard deviation for the populations. Cohen's D is in terms of the population parameters. But for whatever reason, we still call it Cohen's D when we plug in the sample statistics. Now look over here at this formula. What do you notice about this fraction? What's on the top of it? The X bars and the S's. This has the sample information in it. What do we call it? G. G is the effect size in terms of the sample statistics. Cohen's D is supposed to be in terms of the population parameters. But APA style and social sciences have gotten sloppy and they call it Cohen's D even when they put in the sample statistics. Now, it is biased when you put in the sample statistics. And there is another effect size called omega squared that is not biased that we probably should be using, but its formula is a lot more complex and SPSS in the past has not spit it out by default, so social scientists have not bothered with it. So Cohen's D is what we're going to use, and we're going to call it D, even if we really should be calling it G. Is that not pathetic or what? Okay, so that's the only part you really need to know up here. There are some other formulas, like if your sample sizes are the same, here's a shortcut formula. If they're not the same, here's another formula. Again, these formulas are nice if you don't have that pool of standard deviation and you're reading another article as part of your lit review and they don't give you Cohen's D, you can use the sample size and T to calculate it for yourself. And these formulas over here that are dealing with the delta, this is more important if you're using that table in the back of the book, which I'm not going to have you do, okay? So on the homework, you're going to be using G power. So for the homework for this chapter, there's no R part. It's all G power for the software. Now on the exam, you will not have to use G power on the exam because you can't do that when you're on Proctorial. I will give you.
So Sarah, the G, we would just, if we don't know like the pooled standard error, we would just use one of the other two formulas and that would give us the whole right side of the G formula.
So you do the G formula, the X, you need to know the two sample averages. And then down here, the pooled standard deviation, that's the formula that's right here. So
Okay.
if your sample sizes are the same, you pool the standard deviation by averaging them. If your sample sizes are the same, you do the good old average where you just add them up and divide by 2. Now, one important thing I need to point out, this SP here, notice there's no square. No square on this one, no 2 subscript. But on this formula, there's a square. So what would you have to do after you crunch these numbers?
Take square root.
Square root to get the unsquared.
So the T part is the denominator of that G formula.
The T part.
The SP, so where it says
the
equals.
SP here is the pooled standard deviation. Now look at these t-tests. That's not the only thing that's on the bottom of the t-test. On the t-test, we're dividing by the pooled standard error, which has part of it as the standard deviation. So for the t-test, we divide by the standard error.
I'm just wondering on your effect size.
Effect size, we do the pooled
right here,
standard deviation.
The over to the right of your G formula, you've got the 2 T's. Where does that fit into the G formula?
Oh, this is just another formula. If you had T, like if somebody else, if you're reading somebody else's article, and based on their article, you knew their sample sizes and their T, but they had not told you their pooled standard deviation.
You could do that instead of
this.
And that would give you the G.
Yes.
Okay, that's what I was unclear about.
These two formulas will give you the same number. It's just sometimes when we're doing our own work, we're usually going to use the means and pooled standard deviation. But if we're reading somebody else's article, they usually don't publish the pooled standard deviation, but we do have the individual sample sizes and the T number. This is the conversion D and G are not equal. There's this like conversion thing, but social sciences usually just call it the same thing, even though it's not. I don't know why. It's something that I keep shaking my head about. Because the book calls it G in this chapter and then it's dropped. And they just call it Cohen's D, whether you use the sample statistics or not. There is some tractor or dump truck out there just beeping like crazy. You guys can't hear that, can you? Beep, 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 beep. It's been like 5 minutes. Go crazy. Okay. Whew, I talked a heck of a lot today. Well, okay. Okay, this is the last slide. That's good because we're on our last 10 minutes. Last high point, really high point. So when you use G power, right? We use our little G power formula and we get an estimated sample size that we need. That sample size estimate is only as good as the effect size we input to it. So if you guess what the effect size is and plug it in and it says you need a sample size 100 and you go get your data, that's only going to be enough if the effect size really is what you said it was going to be. So you want to be conservative and careful when you do effect size power analysis. And that effect size is really not a good idea to use Cohen's cutoffs of 0.2, 0.5, 0.8. It is better to really dig into the literature that you can find, and it might not be for the exact scale, for the exact population, but you want to look for related populations with related measurements. What's something that would be in the realm of possible and important for the thing that I'm studying? Remember, Cohen's cutoffs of 0.2, 0.5, 0.8 are just general kind of rules of thumb, kind of give you kind of an idea of what would be smallish, mediumish, largish. It doesn't tell you what's applicable to your situation. When in doubt, this doesn't really work so well when you're doing a dissertation, but if you're going to be writing a big grant to a national organization, you're going to want to go get pilot data, like a small set of data, to get an idea of what your effect size is going to be so that you have some evidence on which to base your power analysis. Now, for your dissertation, it's hard because you don't have time to do a pilot study and then do another study. But sometimes with a dissertation, we're able to say that the dissertation itself is somewhat of a pilot study on which your mentor or yourself when you graduate are going to base a greater study. Because a lot of times with a dissertation, we don't have the money, time, or resources to get a huge sample. So sometimes we're piloting for proof of concept and effect size type measures to base bigger projects on. Okay, we've got 7 minutes left and I want you guys to ask me questions because I've said way too much today. What are the things that still don't make sense and are kind of catching in your brain or you're thinking about?
Are we going to be determining intervals for the effect size like they did in the book?
Not generally speaking, no. I forgot to turn on record.
It's recording.
And it's the one time we had a student that couldn't make it because of something else.
It says it's recording.
Does it?
Mhm.
Did I? Oh, I didn't stop it during the break. Oh my gosh. Oh, panic attack there. Oh.
Sorry.
Oh. I'm so glad. Thank you. Okay, questions. Back to you guys.
I'm still confused. I mean, I understand that the smaller the effect size, the larger the sample size.
But it doesn't seem right.
But I still don't understand why.
Can anyone else give it a go at explaining it? Or is everybody still
I was just going to say, if you have a tiny effect that you can barely tell the difference between the two means, you're going to have a huge sample size to justify that. Like a tiny effect is not going to be significant with a small sample size because that could happen just by chance. So your two sample sizes, if they're tiny, that a tiny effect size is going to happen by chance just because you don't have a strong large N, right? So if you have huge effect size, likewise, you don't need a large sample. So if your effect size is really huge, then your small sample is going to pick that up really quick. So to really see a small effect, you've got to have a huge sample size. Otherwise, it's just chance error.
What if we were trying to prove that drinking alcohol inhibited your ability to reaction time? Does alcohol affect reaction time?
Yes.
Does it affect it a little bit or a lot?
Depends on how much alcohol you consume.
This is true. So what if we're talking about, I don't even know what's a lot, maybe 4 beers? Will 4 beers affect your reaction time? Like if we're measuring like ability to walk on a straight line even, let's say the straight line walking test.
Yes.
Is it a little effect or is it a very obvious effect?
Obvious.
Obvious. So if you wanted to prove that with a statistical test, how many people would you need to compare drinking versus not drinking? If you had 3 drinkers and 3 non-drinkers, could you be able to tell the difference between who was drinking and who was not drinking on a walk the line test?
Yeah.
If it's a drastic difference, just a couple of them, and you're like, oh yeah, I see that there's a difference there. What's something that would what about if we only made it drinking 1 beer? Would we be able to tell the difference with 3 people and 3 people? Maybe not. Maybe we'd need like 100 people that drank 1 beer and 100 that didn't to be able to tell the difference between the 2 groups.
So is the effect size like the intensity of, oh yeah, I mean, I guess I'm going to answer my question as I say this, but.
No, that's why I'm asking you to say it.
So the effect size is, yeah, the intensity of which we're implementing the experiment on the experimental group. Okay.
Yeah. So sometimes the effect is set. Sometimes we can influence the effect size by, like, if we're saying drinking the alcohol, you said it depends on how much you're drinking, right? It depends on, the size of the person and how, what's their tolerance and stuff like this. So if I was studying alcohol, and I only could afford to have a certain number of people, would I only want to do 0 beers and 1 beer, or would I maybe want to increase the dosage and do 0 versus 4? I mean, you've got to be ethical. But if I'm looking at a reading program for 2nd graders and I only can afford to test 30 kids, 15 and 15 in a standard teaching method and 15 in a new method, if I have a limited sample size, maybe I would want to increase the duration of the study to give it longer to have an effect, or I might want to have them, instead of doing it 10 minutes once a week, maybe do it 10 minutes every day of the week or 30 minutes to increase the intensity to bump up the effect size if I'm limited in my sample size. So there's multiple players in power analysis. The power usually is 80%, alpha is usually 0.05, usually 2 tails. But that leaves sample size and effect size. And they have this relationship together that the bigger the effect size, the smaller the sample size needed, and vice versa. So sometimes we're restricted in effect size because we're doing a program and it has a certain effect and it only is supposed to be taught for 1 chapter or something. Sometimes we're limited in the sample size because of the time and energy and money and resources we have available to us. So we want to do the best we can. We want to get the biggest sample we can and the biggest effect we can to have a bigger chance of being able to declare something statistically significant.
Okay.
Does that help?
Yes.
There's some examples on the homework. Now, the homework for these 2 chapters is not up yet. Those atomic assessment assignments are taking me like 10 hours to put together each chapter. They're really long, but I think it's going to be worth it because you can check your answers and it auto grades for future semesters. But if you ever think that you're getting an answer marked wrong on a homework, please email me, because it might be my answer key because it's so clunky and time consuming to get set up. But I will be setting up these last 2 chapters in Canvas today. They're started, but how can you start the homework before I get my button gear? You can go to this table and you can, this middle column, get the PDF and do them pencil paper style, or just bring this up on your screen and write it on a piece of paper, or print them out and write on them. This is exactly what I'm putting into Canvas now, other than changing it so it's easier to auto grade. Okay.
Can we adjust the due date for that to give a little bit more time?
Yes. So that's the last thing we need to talk about is due dates, because exam 2 is supposed to open today too, right? Who's ready for exam 2? Yeah. Yes, we are. I'm all about making things realistic. So let's go into the syllabus and look. Here we go. Get my note paper for our class. Okay, so today before class was supposed to be discussion boards for chapters 7 and 8. Did we get those done? Okay, so tomorrow is supposed to be the due date for homeworks 5 and 6. Are we doing? I've had 2 people email me about 5 and 6. Is everybody else going okay on 5 and 6? Or are we just leaving it till the due date? I don't know. I'm worried. 7 and 8, you can do pencil paper, but I'll have them electronically tonight in the exam. So how can we shuffle this? Should we make these due Wednesday night and then these discussions due Friday like we did last week? Would that work? Okay, let's do that. Now we're gonna have office hours. Oh, tomorrow's office hours. I can't do them at night. It's my daughter's 13th birthday. Office hours, is there a better time tomorrow before noon? Anyone? Anyone want to throw out a time that works for you? No one can show up. It's not any good for me to hold it.
Yeah, I'm flexible.
Flexible, Brian? Lara?
I'm flexible.
Hillary, do you have a preferred time?
Anything works for me.
How would 10 o'clock? Is 10 o'clock okay? Let's go 10 o'clock a.m. Tuesday, tomorrow, for office hours. I'll send out an announcement. We're going to bump all of these homework 5 through 8 in the exam to Wednesday, and the discussion.
Could we bump the exam to Thursday? Just take so much time to get the 2 homework done.
Yes.
Thank you.
Yes, we could.
I appreciate that.
The problem is then we're getting into homework 9 and 10. I don't want to be like putting off, so eventually it catches up with us. But we do have good news. Next week on Monday, no class because it's Memorial Day. Okay, so if we bump the exam due date to Thursday, if you guys need to jump off, it's okay. We'll just keep finishing this up and I'll stop the recording.
So is there still an exam next week as well?
There's not an exam the next week, is there? Let's see, where's this one? Oh, I've got to look at this one.
We have exam 3 on the 27th and 28th right now.
Okay, so no, yeah, it's not till the 28th. Yeah. So next week, so today we did, what day is it? Does anyone know? I don't know.
It's the 18th.
We did this Monday, and then Wednesday this week we do 9 and 10, which is correlation and regression. And then Monday there's no class, and then next week on Wednesday we have the t-test, so it's not till the 28th. And this one we can, 28th is a Thursday, so we can bump that to Friday. Yeah, I'm gonna put this over here.
I mean, we could even have,
Yeah. I tell you, every summer I'm like, this is so insane. Why do we do this? And then it comes around, it's like, oh yeah, summer, it's okay, I've done it before. And then always I get into it, I'm like, this is crazy. Why do we do this? Okay.
It's still crazy.
But you guys are gonna be done in like 4 weeks.
so worth it.
Like,
I'm unsure if it's worth it.
is it worth it? I don't know.
I don't know.
Okay. All right, so I got the exam bumped. I'm just gonna keep bumping these.
Just a quick question, Sarah.
Yeah.
When are we going to get our grades back for the homework 1 through 4 and the exam?
And exam 1, the reason I haven't graded them is because I've been making your new assignments. But
Okay.
the good news is this is not how it's gonna be the whole way. Because once we get to chapter 10, the atomic assessment's already created for the second half of this class.
Awesome.
So I apologize that you're like, you guys are probably on pins and needles just waiting for your grades, right? No, you probably don't want to know. No, you guys, I'm sure you did great. But I will be getting those graded. I just have been trying to get these atomic assessments up for you guys. But yes, I will get those graded. I was going to have them done on Friday. That was my goal. And then homework 6 took too long. Okay, I thought that I moved that one. Did that not move? Oh, it did. Look, it's there. What did it do? Oh. It only made it for Colleen. I don't even know why I did that. Did everyone leave me? Where did we go? Oh, there's everybody. It moved you guys over there. Where is everyone? Okay. There we go. There we go. Okay. We said Thursday. No. Which one am I on? Did I click on the wrong thing? Oh, this is homework 1. Homework 5. There we go.
Is it still beeping over with you? Are they still beeping? I thought I could hear
No,
it.
but it's beeping somewhere else.
Oh, I was like, holy crap, that's still going on?
No, it finally stopped. It was like seriously forever. I was gonna go insane. But it's quiet here on campus other than that. Like nobody's here.
I feel so much better after the lecture about
Do you?
chapter 8.
Good. Now, I always find whether you read it first or lecture first, the second one always clears it up a lot more. It's that multiple exposure. By the time, if you've done both of those and then start doing the homework, it starts to gel. But one of those things alone is not enough.
I was wondering if I needed to drop the class today because it was the last day to drop after morning. It's like, I don't know if this is possible.
It's possible. You're going to make it. You're all going to make it. If you're not, then I might need to change something. You guys are capable. Did you guys all see on the homepage of our class that I put up my favorite comics or memes or whatever, the learning curve that I showed you, and then the imposter syndrome one? Those are there for your perusal. Okay, so we got exam 1. Did I bump those to the right? Or exam 2, sorry, exam 2, and the homework's bumped to Thursday. Today's Monday. So you have those discussions. And then this one, Wednesday, before we talk about it in class. And this one, we're gonna bump to, well, we don't have class on Wednesday. We could even bump this to Tuesday because we don't have class till.
Wait, the 9 and 10 discussions we do on Wednesday?
Yeah, because Wednesday we're going to talk about those.
I thought we were bumping those to Friday.
We're gonna bump those. Yeah, we'll bump those to Friday. It'll be after we talk about it in class, but I can deal with that.
That seems to work for me.
Oh, that's not. How did I not get to the? Oh, where edit? There we go. Friday. I don't want to kill anyone off here. It definitely would not be beneficial.
This class is making me wonder why I wasted so much time in grade school learning math instead of statistics.
Yeah. There is some movement to, instead of do calculus in high school, to do statistics instead.
Yeah.
Yeah. There is AP stats is being offered more and more, and the 1040 stats is concurrent enrollment around these parts too.
Yeah.
My daughter will be taking, let's see, did we get 9 and 10 to, so it's Thursday, Friday, Monday's off, so that Wednesday, I think, will that work? Are we good now? Okay, let's go with that.
Thank you guys.
Okay, please email me if you're having questions. Office hours tomorrow at 10.
Okay. Thanks,
Okay.
Sarah.
Okay, we'll see you guys later.
Thank you, Sarah.
Stop recording.